Okay, so thank you all for attending. Um, I'm David Barr. I'm the head of the School of Materials Engineering. And for the next half hour or so, I'm going to talk to you a little bit about some of the things in materials engineering. Supposedly, you've all watched the video clip on the Purdue YouTube clips about the program, so there should be some information that you already have a little bit. Materials, we like to say you can't make it without materials. And fundamentally, that means that if you can't grow it, you got to make it in some way. And so what we do as a major is we're the engineers who make the stuff that other people make things out of, okay? And what I'm going to do today is I'm going to talk some about, where students go. And now I got to figure out how to move my pointer thing. And where students are at, okay? So with that, just want to share a little bit about myself first to start with. I actually I was sitting where you were 30-ish years ago in a somewhat different room, and probably we were in person because we weren't doing it online because we didn't have this internet thing. We did have email though, so it wasn't quite that old. But I did my BS and MS here in Materials Science and Engineering at Purdue. I went to the University of Minnesota for my PhD. I spent some time at Sandia National Labs, and the work I did there and starting off at Washington State University led to a PCASE award. It's my only opportunity I've had to to tour the White House and supposed to, and get to a Presidential Early Career Award. It was a fun experience. I went to Washington State University and I went to the School of Mechanical Materials Engineering at WSU. I became the director of undergraduate research for the university, and then I became the department head for the School of Mechanical and Materials Engineering at WSU. In 2012, I had the opportunity to return to Purdue, and I moved back here as department head, and I've been here for the last 8 years. Okay, so I want to tell you a little bit about materials science and engineering as a whole, okay? So as I mentioned before, we make the stuff that things are made of. So we may design new materials that allow us to do new designs. We may modify, improve, or just make more efficient the way we make existing materials. We may analyze why materials work, or very often, just as importantly, why they don't work. And we develop processing methods to reduce energy use, which often translates directly into cost, but it has a lot of societal implications about that also. So what I work on as an individual is I break little things. I do small scale mechanical research, and we test some things because they're small and others because we can characterize them well at that scale. We all know how to make a better jet engine, how to make a more efficient turbine engine, run it hotter. The problem is we actually are at temperatures now in turbine engines where the materials have to operate above their melting temperature. And let that kind of rattle around in your head for a second. The solid part of the fan, if you did not actively cool it and have a coating that kept it from the very, very hot portion, would melt. And I can suggest that the fan blade wouldn't work as well if it was a liquid spinning around. So we actually use materials that separate the hot zone from the underlying material that if they fail, the whole thing fails. So we know that we're currently operating a lot of materials, high performance materials, at their limits, and we want to be able to extend that. Materials design means we want to be able to screen things. If I change something this way, what happens? And one of the areas that I work in is how to test these small features, because a lot of the materials are very expensive and it's hard to get enough of the initial batch of experiments when you're doing material design to know if you should go ahead and invest the $90,000 in the next experiment. So if we can do that faster and smaller, then you can do a lot of iterations before you have to go through and do the investment in a larger scale, right? And so if you think about the range of atoms to aircraft, So it's hard to measure properties of individual atoms and is expensive to build an aircraft and go, wonder if that'll work. And so the right place to test the properties of materials and how materials perform is either on some sort of small scale where you have some subset, we've stacked up enough atoms that we have a piece that is effectively representative, or in kind of a component mode where we can watch and see, oh, what kind of stresses or what kind of environmental condition is present at that spot, and then assess the properties at these length scales, as opposed to getting all the way up to this or trying to go through and move an individual atom at a time. We do study individual atoms, but it's in relationship to how they add up here for materials. Okay, I'll show you just a quick example here. We work on a material. This was a oxide that was grown on stainless steel and titanium. And the material was grown, this was done in conjunction with Sandia National Labs, where we were trying to make the equivalent of a QR code over a welded structure so you could find out if anyone had broken the weld. I assume people remember or have seen, if you go kind of Game of Thrones, people would send messages where they wrote a message and then they stamped a wax seal to prove that it hadn't been opened. The ability for us to grow a colored oxide on titanium or stainless steel is kind of a modern version of the wax seal. Now, the problem is the oxides we grew on these materials to make sure that they hadn't been tampered with led to cracks in the material, and these cracks might propagate down a few microns. Just for size scale, to remind you all, your hair is about 20 microns in diameter. So this crack runs all the way like 1/5 of the diameter of your hair, which is not very much, except if it happens to be that the part you were sealing is in a really harsh environment, this crack may lead to some problems. And so we study how things break and how things deform on a small scale. We test materials that are hard to test on a macroscopic case. I show here 2 examples of energetic materials, explosives. These are materials that we want to know if a change in process changes their properties. And we'd like to do it on an amount of material where if there's a mistake, nobody walks out of there nicknamed lefty. So if a piece of RDX that small, on the order of a couple diameters of your hair, is put under a large pressure, it can't explode. It can burn, but it actually cannot explode. It's too small to build up a shock wave that leads to an explosion. So testing small materials sometimes is a safer thing to do than testing a big vat of something else, okay? And we do that from energetics, and we also do with pharmaceuticals, where just the sheer expense of making large volumes can be a problem, okay? So that's a little bit about me. So let me kind of walk through the field as a whole and what materials and how materials kind of shape up within the scope of engineering as a whole. So like I mentioned earlier, we like to think that we work somewhere in the intersection between atoms and aircraft. For those of you that, were alive in the early 90s, maybe none of you, there was a series of ads from BASF that used to say, we don't make the surfboard, we make it stronger. We don't make the car window, we make it brighter. And that's kind of what a lot of the MSEs do. We don't necessarily make the chemistry, and we don't necessarily make the final piece, though often we're involved in that. We decide, so if you're trying to look at, well, what's the yield on this chemical reaction? Yeah, that's not us. And we don't necessarily design the shape of a plane with new composites, but designing the composite material that's used in the plane, testing the new composites to see if they meet the specifications and how you can form them on a scale that's engineeringly appropriate, that's what we do. So to make a composite, you would need new chemistries, you would need new processing technologies, and a materials engineer kind of puts them together into how do we form these structures and how do we form materials that have predictable properties that people can design with. And we also work on the fact that not all materials properties stay the same throughout their lifetime. We have to be able to predict degradation. We have to be able to pick performance. In many big engineering applications, whether or not the plane flies on day 1 isn't necessarily the most important question to you if you're flying on the 13-year-old plane. You would like to know that it's as safe as the one that was made on the first day it came out. Okay, so we develop materials that improves people's lives. We also develop materials that people have fun with. So if you think about just something as simple as a bicycle, you go back and you look at a picture from 1890 of a bicycle, and then you look at a picture today of a bicycle. Hey, they have two wheels. They got a frame that kind of looks like a couple of triangles put together. There's a seat, there's some handlebar-y things, there's a brake, you got pedal. Yeah, they pretty much look the same. But the weight difference and the ability of a material, in this case, a high performance bicycle that's used for competition and can set you back the same price as a car. This kind of development in how do you go from the basic design to something that's truly pushing performance limits, that's something materials people do. In a similar way, this bicycle was more expensive to manufacture in 1890 than it is today. We've constantly driven down the price of materials, we've driven down the flaw density, we've driven down the variability, such that you can make the same bicycle over and over in a more efficient manner. And the end result is something that's both more efficient to make, uses less energy, has a smaller environmental footprint, and is healthier for everybody. Okay, so we can work on materials that are fun too. As an example of when materials engineers do something other than designing a new material or how to process a material, sometimes we have to take a look at why materials didn't perform the way they're supposed to. The Aloha Airlines flight in 1988 is a good example. For those of you that have watched things like Engineering Disasters on the History Channel or something, this is the flight where a third of the airplane basically popped off during flight. There were a lot of bad things that happened, and there were some good things that happened. One of the very bad things is one of the flight attendants lost their life because when it came loose, the flight attendant fell out of the plane. One of the impressive things is the rest of the system and the rest of the materials performed well enough that they could safely land, only having one person lose their life. The entire thing was caused by a fatigue crack that happened every time you take off a plane and it's pressurized for your convenience. The plane acts a little like a balloon that blows out, collapses back, blows out, collapses back, every takeoff and landing. And that repeated cycling on aluminum causes the formation of small cracks. And a crack is a stress concentration, which can lead under pressure to a crack that continues to grow. And as that crack grows, the stress goes up and the crack grows faster. And in this case, the crack grew catastrophically. And once it started, it popped a third of the plane off. So how do you develop a material that has better resistance to fatigue growth? Or how do you develop an inspection schedule that says, we know what that critical flaw is, and that's the one we have to be able to go find? Because when you deal with something as complicated as a plane or a rocket or a locomotive, really big structures, there's going to be variability, there's going to be potential flaws, and how do you identify and find them is an important part of what we do. Okay. Now, so hopefully now you have a little bit of sense about what we do out there. Let me show you a little bit about who we are within Purdue and within the nation. So, do any of you know how many how many first-year engineers there are this year in your class? And because we have like 300 people watching, I am not going to ask for people's hands. But just to give you a quick sense, there's about 2,500 of you kicking around this year. Nationally, for the entire country, we graduate about 1,800 MSEs. So to give you a sense, Purdue brings in more engineers each year than the entire country outputs for materials engineers. So we're a relatively small discipline. We graduate between 50 and 70 MSEs a year within Purdue, which means we put out a few percent of the nation's engineering MSE population. So we're small on campus and we're big on a national scale. So we're not putting out 1% of the nation's MSEs, we put out several percent of the nation's MSEs. So we're a relatively big player. We're about the 5th biggest to 6th biggest MSE program in the country. We also have about the same number of undergraduate students as graduate students. We're a research-heavy endeavor, okay? And that comes out in some of the activities that our students participate in. We're about 35% women and about 12% underrepresented minority students. We were ranked 11th in the most recent U.S. News and World Report ranking. So we're just below Penn State and Carnegie Mellon and just above Caltech. So that kind of tells you the community that we play in. We play with both large public institutions like Penn State or University of Illinois, and we play with private institutions that have much smaller student bodies, Carnegie Mellon, California Institute of Technology. Our graduating student to faculty ratio is about 2 to 1. We have about 30 faculty in the department, or like 33, and we graduate, between 50 and 70, so round numbers, 60 students. Most of the engineering disciplines are significantly higher than that. So we're a department where you're going to have a lot of interaction with faculty. That can be good or bad, depending on what kind of interaction you have. We are not a department where you can kind of hang back and not get noticed. Hopefully you get noticed for the right reasons, okay? We have a growing list of expanding co-ops. Every year, there are more people that ask us for MSE co-ops than we have students in the co-op program. So there's demand that we haven't been able to meet. We have campus leaders in entrepreneurship. MSE teams have won the Burton Morgan Business Plan competition not the last couple years, but over the last 5 years, they've won it a few times. And we have all types of materials represented. Materials is all the things around us. We have metals, ceramics, polymers, composites, electronic materials, biomaterials, natural and environmentally sensitive materials. So the extent of what we do, whether it's for designing a material for new lasers, to designing a material for a window, to making a lead-free faucet so that the casting doesn't use any lead and improves water quality, the materials we do impact all sorts of different types of materials. And then in terms of applications, it's everything from energy and power generation to consumer goods to structural applications to high performance electronics. Okay. Our undergraduates in the school come from around the country. We're about 50% out-of-state domestic, 15% international, and about 35% from Indiana. So Indiana is our largest population, but is not the majority. So we're a state school, but we're not just Indiana and MSE. And that's true, you'll find pretty much across all of MSE. One of the features that is particularly interesting, hopefully for you, is that when we talk to employers, they say over and over, one of the reasons they like to work with Purdue is they can find students from all over, be it all over the US or all over the globe. And that's because they like hiring Purdue engineers, but they know it's easier to get students, particularly for large multinational corporations. People are going to move. People are going to be stationed at different locations, and Purdue students come from a really broad range across the country and across the world. Okay, so we make stuff. We take a very hands-on approach. It's a laboratory-intensive curriculum, and about 50% of our undergraduates do hands-on research with faculty members. So in 2018, it was 52%. 2019, the 1920 school year, I'm probably not even going to bother reporting numbers because nobody can tell exactly what happened after March, but we were on track to have about 53, 54% of the undergrads involved in research activities by the time they graduated. And as I mentioned, our co-op program is growing, and about 75% of the students have either done a co-op or an industrial internship before their senior year. So we have labs through sophomore year and junior year, 235, 335, 367. We have students doing undergraduate research. This is Jerome measuring some properties. This is actually measuring surface tension of the materials. We have students working on aluminum castings and casting new alloys. So there's a lot of hands-on kind of lab activities. But And as I mentioned before, we have about the same number of graduate students doing research as we have an entire undergraduate population. And in materials, as a country, we graduate similar numbers of graduate students and undergraduates each year. And so a lot of our students are looking at that choice of, do I want to get into an R&D career? Do I want to get into production or quality control or failure analysis? What type of engineering do I want? And so students have hands-on experience, and we let people count up to 6 credits of research as their technical electives also. So a lot of people try an internship with a company and a research experience. We have numerous study abroad activities that someday will occur again. They don't matter now, but in the future, we have a strong partnership with Imperial College in London. That's probably our most popular program. And then several short courses in Brazil, China, and Spain. Okay. So I mentioned we do a lot of labs. During the sophomore and junior year, there's hands-on organized lab courses. Senior year, we require 100% of our students do a senior design experience. These are industry-funded projects. They're real teams with real impact. As an example, a few years ago, we worked on a project with Arcelor where the students, they were having a problem that cost them about $250,000 a year in wasted product from one of the mills up in Chicago. And the students did a design of experiments. They tested which of the 6 parameters was most important, and they identified there was one. There was one of the parameters was causing this scale problem. So this is steel that gets turned into wheels for cars, and if it oxidizes and forms a kind of rough scale while it's being processed, then the wheel doesn't look pretty, and Ford sends it back to Arcelor and says, that coil is garbage, send me another one. And it happens sometimes, not all the time. And so those are very nagging problems. How do you fix a problem that only shows up sometimes? So the students did the design of experiments, figured out what parameter was most important. It turned out it was the relative humidity in the furnace. Arcelor engineers were able to go back and actually look at the weather at the mill and find out that, oh, lo and behold, on humid days is when they had their problem. So the solution was basically fixing the air conditioning to fix the steel. And the students do, we've seen projects at Howmet, which is Alcoa Howmet up in Whitehall, where the design the students have used for heat treat baskets has been fully implemented and saves about $100,000 a year for the company. So the students work on real projects that do get implemented out there. Okay. So after graduation, what do our students do? Well, about 70% of our students go off to industrial jobs. About 25% go to fully paid graduate research positions, mostly at the PhD, some at the master's level. And then about 5% are still looking after they've turned down something. If you're ever interested in looking at the different departments, I recommend, CCO puts all this together, so feel free to check us all out and compare an apples to apples kind of comparison. Our recent average salaries are about $70,000. And people going to manufacturing, aero, automotive, and health and pharma are kind of our biggest chunks right now. But the key thing is there's no normal. So, if we have 60 students graduating and 45 are going to industry, they go to 42 different companies or 43 different companies. We don't have a typical MSE job path. We have as many job paths as we have students. And that can be a little daunting as a first-year student, because if someone asks, well, what would you do? And the answer is, well, what do you want to do? But I want to be able to describe what I know. We're going to help you find what you want to do and be able to do it. And so that can be a little scary because you're making your own path. But what you find is materials people don't get hired en masse by one company or another. We may place 2 people at Arcelor this year, 1 person at Alcoa, 1 at Ford, 1 at Boeing. We may place people that are making insulation for your house, or they might be making bottle caps. We place people that are doing failure analysis and certification for things that are being launched into space, and people that go work at Intel on packaging chips to handle high thermal environments. Okay. So a few of the companies people went to last year, as we mentioned, might be Arcelor or GM, Berry Global, that's polymers company, people making gears, people making engines. Cummins should be on there somewhere. They hire somebody every year. People making raw materials, people making jet engines. So there's no normal. And We have a couple nice phrases. One of them is you can't make it without materials. And I think more and more the fact that we're not normal is probably our next best one. So people go design new materials, they make them more efficiently, they lessen the environmental impact of materials. They often work in teams for material selection with project design and product design. People go off to government agencies, people go into teaching, and then people do testing and validation. Now, let's see if I can. So here's an example from Catherine, graduated a couple years ago, works for Procter & Gamble. And you know, what she was looking, as an example, they want to make sure, oh, they've changed the chemical, and they want to make sure that chemical, i.e. the soap, isn't going to result in corrosion problems when they process it. She also was working on something tied into food processing. Corn is more abrasive than potatoes as you grind it up. And so you have to be able to select materials that have better wear resistant so they don't chew up the platens that keep putting out the same material. Now, I'm going to try something here. We'll see if I can do it or not. Okay. I'm going to not share that. How do I stop share? Seriously. Hang on. See if I can, oh, curses, foiled again. Let me see if I can get a new share to start here. I am, okay. This is probably going to work. What I'd like to do is I would like to try to give you a little clip of one of our recent students who is working at Bridgestone. And so we asked Sarah to give us a little short video. So I'm going to try to play this and we'll see if it works.
Hi, my name is Sarah and I'm a materials engineer for
Hector, could you give me a thumbs up if it's working?
I work in between research and manufacturing. Working. I work on both bringing in new technologies into mass production while also improving upon our current and existing products. Materials engineering for tires has two specific categories. We have our reinforcing materials and our rubber compounding materials. For reinforcements, we have different fabrics, nylon, polyester, rayon, things like that. And we have our steel components, which are plated in either brass or bronze to help adhere to our rubber components. The whole purpose of our reinforcement materials is to provide durability and dimensional stability for our tire. On the rubber compounding side, we have to bring together all these different raw materials or ingredients, mix them together into a homogeneous rubber sample, and test those physical properties because for a specific design target. The base of every formulation is our rubber or our polymer. We have to work with either styrene butadiene, polybutadiene, or other synthetic rubbers that we make in a lab, or work on our natural rubbers, which come from the latex of specific trees. So depending on which application we're looking into, we have, for example, our passenger tire, which is a cross section here. You can see all the different layers and components. Each of these components is a different formulation or different compound. For a passenger tire, you can have up to 15 different formulations. And each formula has a specific purpose. So whether you're trying to improve your cornering, your fuel efficiency, your wet stopping distance, things like that, will change your formulation. So a typical product that I would normally get is if I were to be given either a new raw material or a new raw material source, I would have to develop the formulation for that. So I would work in our labs downstairs to design a formula on a small scale, so maybe 3 to 6 pounds of material, test those properties for modulus, tensile, cracking, ozone, different things like that. Once I have selected a specific formula, I would put it into manufacturing, again, at a smaller scale. So I'm only mixing and manufacturing maybe 1 to 3 pounds, or 1 to 3,000 pounds, of material. And we would test that again to see if the manufacturing side of things can meet that design target that I saw on that small scale. Once we have done that and we have proven the actual feasibility of it, we actually build a tire. So once we build the tire, we have to test it either on a track or a drum to make sure that whatever tire performance or tire performance metric that we're looking into is either improved or stays the same so that the customer is happy or satisfied with whatever tire we put in the market. And so that's kind of the gist of what I do for materials engineering. It's a really cool job, and I work with a lot of different people from tire design groups, research groups, manufacturing, procurement, quality, just engineers from all around the world, really. But please consider materials engineering and boiler up.
Okay. So I'm going to just finish up here one last second with, I'm going to leave you with a few thoughts here. So if you're interested in more information, well, if it was 3 weeks ago, I'd say you should rapidly enroll in MSE 190. It's a 1-credit course. It's fun. But if you have questions about enrollment, our academic advisor is Vicki Klein. There is not a question about academic advising that Vicki has not had before, and she will be able to help navigate things through. But really, if you want some more information, one of the things I'd like to do is have an opportunity for you to ask questions. So we have a couple MSE students with us. So if, let me unshare here. My ability to unshare is really bad. Okay. So we should have a couple MSE students with us. I don't know if they can unmute themselves.
Yeah, I can.
Okay, so Chadwick.
Hi, I'm here.
Okay, and Riley's here. Okay.
Hi, everyone.
I'm sorry, I just mispronounced that. I apologize. So what I want you guys to do, if we can do this, oh, the QR code comes at the end. It's not the end. This is the end of me, but not the end of our presentation. So what I'd like you guys to do is, I'm assuming you may have questions. Out of 300 people, if we have a question other than where our QR code is, I think the students would be happy to do this. Can you guys see the chat? Yeah.
Yes, we can.
Okay. Yep. And just to show how much we truly trust all of our students, I am going to leave so that you can know that you're getting the honest truth. I have no idea what they're going to say. They may describe me as a complete and utter buffoon. And if so, thumbs up there. But I want to give you guys a chance to be able to ask real live materials students questions. So I'm going to go ahead and disappear so that I'm not influencing the attendance. Is that okay? So that good with my MSE volunteers? Thumbs up? Okay. Okay, so I'm going to disappear and I will.
A lot of trust. But...
Happy to, and if you have any questions for me, my email is dfbar@purdue.edu. Feel free to send me an email separately if you'd like afterwards. However, I am sure they're going to be able to handle your questions. Okay? So, adios.
Bye, Dr. Professor Barr.
Hey, guys.
Hi, everyone.
Hello.
So I guess we'll just start going through the chat and answering questions.
Oh,
one that's really standing out to me. Oh yeah, we should do introductions.
Yeah, we should do introductions.
I'll start. Hi, my name is Riley Plotner. I am a senior in materials engineering. I was in your seats in fall 2017. I actually came to Purdue wanting to do chemical engineering. Hadn't even ever heard of what materials engineering was, and just by like a stroke of chance, I signed up for MSE 190, which is really what made me realize that MSE is a lot more applicable to what I want to do in life and in industry. So that's how I ended up here. I have been doing research with a faculty member for the last 4 semesters. So I know a lot about undergraduate research, if you guys are all curious about that. I've had a couple different industry experiences at first BAE Systems after my sophomore year, and then GE Aviation this past summer. So I'll pass it on to Chadwick now.
Yeah, I'm Chadwick, junior in materials engineering. Again, MSc wasn't on my radar. I actually wanted to be an environmental engineer, but then I realized they don't do that as many cool stuff as materials. I've done research ever since fall of sophomore year, and I've recently just got a co-op with Kimberly Clark, so you can get to places, definitely. Cool. First question? Yeah.
And then is it just us two for the materials engineering students, I think? Okay.
Yeah, okay.
Let's get into it. One question that's really standing out to me for the chemical engineering and materials engineering, and just kind of like materials engineering overall and why I chose it. I came in wanting to do chemical engineering, but one thing that I didn't realize is that, so my favorite thing throughout high school was chemistry. That was kind of like my passion, but I knew I wanted to be an engineering student and an engineer later on to solve problems. So when I got to Purdue, I realized that chemical engineering is a lot more math-based. So for pretty much how I think about chemical engineering is scientists will create something in lab, and it's the chemical engineer's job to take what is created in a very, very small lab and blow it up full scale to mass produce in an industry production. And that didn't interest me too much because I wanted to be able to focus on actually improving substances rather than just figuring out how to mass produce. So for me, that's why I was especially drawn to materials engineering, because there's so many different things that need to be improved right now in industry. I know Professor Barr had mentioned jet engines, about how they constantly want to make it hotter, and the materials that are used inside jet engines, they operate at melting temperatures higher than their own. So there's a lot of research going into materials about how to make things better, how to improve, constantly pushing the boundaries. And I really want to be on the forefront of that design so that I can know that I'm helping society advance tech, like in a technical matter, you know? And it's so applicable to every single industry. So regardless of if you want to go into the health industry, like materials encompasses every single kind of like passion that you could have outside of school. So for me, I want to go into aerospace and defense because I love planes. And from there, I'll be able to help continue and improve the materials used in that industry. What about you?
Yeah, I can build onto that. So I would say definitely chemical engineering is more of the process and scaling it up. And materials engineering is more focusing on what we're using to make products out of, and what we're using to actually like influence the entire life cycle of anything in general. And when I was scrolling it through, like one of the questions I saw is, why did I choose MSE? So I chose MSE because of the fact of it kind of plays into what I want to do in the long run. And to give background, I'm from Hawaii. So yes, MSEs come from everywhere. And with that in mind, it was just more of an impact of just me wanting to try and make products more sustainable, make them less petroleum based, so that we don't end up things with like the Great Pacific Garbage Patch. Anyway, and MSE really just gets at the bare bones of it, right? You can design good materials, then it's gonna have a trickle down effect. It can affect airplanes, it can affect even your iPhones and the cases that they're made out of, right? It's the small details that really do make the longest difference in the long run. And the reason why I didn't go into anything like aero, mechanical, chemie was also because of the curriculum. Because if I was doing chemie, I would be doing like fluid, like all these calculations. I would also probably be doing a lot more heat transfer, mass transfer, and stuff like that. Whereas in MSE, you really get like a full rounded thing. You get crystallography, you get, which is the study of crystal structure and like how they refract it. You get like quantum mechanics, you get thermodynamics, you get statics, fluid flow, heat transfer, electrical, magnetic, optical. You get like the full range of things. It's a lot more physics than you would expect from chemical engineering. And that really did intrigue me because I wanted to be well-rounded and not just focus on just one thing. Like I'm really good at mechanical, like stuff like that. You can just dabble in different areas. It's really fun.
Yeah, Yeah, that's what I really like about it. And I'm noticing that a lot of questions are asking about, oh, can you do this with MSE? Can you go into this industry? Like, what are the most common industries? It is, materials engineering is probably the most applicable engineering discipline, and the most, there's just such a broad range of things that you can do. And I mean, Professor Barr put that statistic up there that there's not many that graduate in a year. So it's kind of a sought after position, because if you go online and look at their job openings, pretty much every single company has job openings for materials engineers, because you can't make it without materials. So if you want to go into a specific industry, it's most definitely possible. I'm seeing some questions about the math that's involved with materials engineering based on what Chadwick said. You take up through differential equations, the ordinary differential equations, which I think is MA 266, as well as you take linear algebra, and then backtracking from there, Calc 3, Calc 1, Calc 2. I said that out of order, but it's not as math heavy as, let's say, like aerospace or mechanical engineering, but you still get to experience a decent amount of math department here at Purdue. Another question I'm seeing that I think I can speak to pretty well is research within the MSc department. Chadwick, do you do research, or have you done research?
Yep, ever since I've been a part of the department.
Okay, so
Research
who do
fun.
you do research with, and what do you do?
Yeah, so my sophomore year, I was under Professor Youngblood. He works with polymers, and he was specifically working with cellulose nanofibrils. So it's basically, you know, trees, they're made out of stuff. That stuff is cellulose, right? And what they do, they basically filter it and fine it down a lot, so you get these nice, like, tiny fibers at the microscopic level. And what I was mainly doing there is trying to chemically enhance it using additives or using cross-linkers. And in an industry-based, like, long scale, it can be used to replace, like, small plastic things, like in a car, on its surface, tabletop. But the only problem with that is that cellulose, which is in trees, has very interesting properties at different humidities, because cellulose is meant to be able to kind of transfer water well. And if you want something strong, you want it to be even strong in high humidities, which cellulose isn't really, because if you think about what a tree is, right? So definitely. So that was my entire sophomore year. During the summer and now into the fall, I'm working under Professor Titus, and we're working on high temperature alloys and kind of accelerating that process using machine learning, and also online using workflows to accelerate the exploration of that area. So you can do like fun things like CS, you can do atomic modeling through NanoHub. And we also have like Burke Nanotechnology. I know some professors do stuff there. They have a huge clean room. It's fun stuff. Yeah.
For my research, I've been working under Professor Chelsea Davis. She does a lot of soft substrate, adhesion, polymer mechanics. And so what I've been working on for the last 3 semesters now is determining if there is a surface energy dependency on strain in this really soft gel material called polydimethylsiloxane. If you guys have ever like had window clings from like the dollar store for like holiday decor on your windows, like that's pretty much what polydimethylsiloxane is. So looking at the surface tension properties of that, just to be able to apply it to certain like adhesion mechanics and all that. And it's been a very amazing experience. A lot of the faculty here, they really trust their undergraduate students to kind of take the reins and be able to run with whatever project they have, of course, with giving guidance and all that in like a structured way, but you really do get to take ownership over your project. At least that's what I've experienced. That's what I hear all the time from, you know, different classmates. It's really amazing what they kind of like trust you to do, and you are like kind of under them, kind of being funded by them while they're doing this. So it's really nice to have that level of responsibility as an undergraduate student, also to determine if you want to go into grad school or not. In terms of like reaching out and getting these research positions, I actually met my research advisor from the MSE 190 course. Highly recommend taking it next semester if it's offered. Like I said, that's how I kind of got into materials engineering. But I met her through that, And then like a year later, she came in and gave a guest lecture in my classroom, and I just went up to her afterwards saying that, you know, I really appreciated it again to like see her and all that. And she pretty much right there, she was like, hey, come do research with me. So it's really just about making those connections from the start. If you approach a faculty member several times, they'll start to recognize your face. You know, if you show that you're passionate and that's what you want to do, it'll be a lot easier to kind of get into the group. Also, if you don't know exactly like where to start, you can always go onto the materials engineering website online and look at the different faculty members and look at their research projects. And if something interests you, then don't be afraid to reach out. Might be a little too soon as a freshman, but it's never too soon to reach out, but it's never too soon to start looking into it, thinking about it, so that you know, like, hey, like this is where I'd like to be my sophomore year. If you reach out like next semester saying like, hey, if you have any openings this upcoming year, like please keep me in mind, like this really interests me, this is what I want to do. So, you know, kind of just to get your name in the door. It's never too late to reach out. Also, I just saw that there are some people who are just starting research projects their senior year. So it's really just about whenever you feel ready, whenever you have time in your schedule. A lot of the times too, faculty members will start the semester and then realize, oh wow, like my plans for this semester, I need an extra couple hands in class or in lab. So I'm gonna go to an undergraduate student and see if like they can help me out. So you'll hear a lot about those opportunities within the first like couple weeks each semester once you get to materials engineering.
I think so. Yeah. I saw like the next one was just like, will you look at the master's one?
Yeah, that's what I was thinking, master's.
I would say any undergraduate course you take in engineering is going to give you the fundamentals. It's going to give you the basic things that you need to just get out into industry. Once you start thinking about masters and PhDs, that's when you get more specifics. You get more kind of detailed things where you're using those introductory courses to actually build onto complicated things like, say, fracture in materials, or also like solidification, super alloys and stuff like that. That's when you start to use that prior knowledge, like transport phenomena, thermodynamics, and all like statics, and building that all together. So masters doesn't have to be your end goal, right? You can always change up your major when you take your masters. You can be like a materials engineer undergraduate, realize maybe it's not right for you, and switch up to mechanical. That's fine. Just know that what you do in your undergraduates doesn't necessarily have to be what you do for your masters. Yeah.
And in terms of, if you don't want to go to grad school, if you already know that, which I believe all of you are way too young to know that, but if you know that you just want to go straight into industry, there are still so many opportunities for that. There are still a lot of companies that will hire R&D positions to people with bachelor's degrees, because even though you don't have that like higher education experience, you still have, you know, the problem solving abilities to work for a company and to look at their problems. You also have a fresh mind compared to someone who might have been working on the same master's or PhD for 2 to 4 to 5 years. You know, so I've talked to a lot of companies about this, and I'm actually planning on going into industry right after I graduate in May 2021. I'm currently interviewing with GE Aviation. Next week is like the final interview for this position I really want, so like wish me good luck. But GE Aviation, and I know this is true for a lot of other companies, they will pay for you to get your master's or even your PhD because they view you as like an asset to the company. Like if you join industry and you know you want to eventually go back and get your higher education, like a higher degree, you can easily do that. Pretty much every company that I've ever worked for and most companies that I've talked to, like they really want their employees to continue to grow with them and get that the higher education so that they can continue to contribute for the company. So that's kind of something, if you're still, by the time you get to senior year in materials engineering, if you're still kind of on the fence of whether or not you want to get your master's or PhD, then it's pretty much never too late to decide that that's what you want to do. In my research group, we might be getting a new PhD student who has been in industry for about 5 years now. So it's truly never too late or too early to really start thinking about that. Thank you for everyone saying good luck. Appreciate it.
But I've seen like things in the past, like about if I'm scrolling through the chat, it's like industry, like what kind of industries can you get into? What kind of opportunities are available through materials? Yeah, I would say that you got your options open, because I've seen things like automotive. I know Cummins does fuel injection, definitely for materials engineering. So that's automotive. You can also work in, if you do like ArcelorMetal, you can probably start doing, or like Nucor, you can probably start doing things with actual sheet metal that's used to make cars. I'm just scrolling through the list to make sure we address everything. Computer processors. I'm taking my electrical and magnetic optics course. Yeah. You got something on that?
Semiconductors are really huge with materials engineering, if that's what you're looking into.
Definitely.
I'm not sure if y'all can hear me. It's very choppy for me right now. Sorry. But something about the automotive industry, you know, like jet engines always want to operate at higher temperatures. For a lot of cars, they always want to get lighter and lighter because that's how you get more fuel efficient. So if you want to work in the automotive industry, there's always more research and development that needs to be done with composite materials, making lighter so that they can be faster, working on the paints that go onto cars, making them be able to withstand the elements better and have like stronger, tougher finishes. All of that is super applicable. I saw someone mention something about biomaterials. Think about like artificial hips and all that, the titanium or like titanium screws that go inside the body. These materials need to be porous so that the body can kind of like grow into it as well. And so that's something that there's always improvement that's necessary there. And if you are like putting materials that foreign objects into your body, you want them to last and not, you know, corrode or anything like that. I can't speak too much for the biomaterial side because I've never really gone into that, but there's always something to be improved in every industry. And even if you don't know where you want to work, and you know you want to do engineering and solve problems, then materials engineering is a very good place to start.
Yeah. I can try to answer this. So do MSE graduates go into packaging, materials, or manufacturing? Not always. They can also do R&D research. They can also do product control, stuff like that. Like for me specifically at Kimberly-Clark, I'll be helping out at nonwovens and kind of developing, I don't know yet, but I'm working with nonwovens. It's going to be at Roswell, Georgia. That's fun. You can find multiple things in research and development. What I found sometimes is that if you really want to start making new materials, that's probably when you need like master's and PhD. But like in some companies, they allow you to do that kind of R&D stuff with undergraduates, which is great. But it's not all manufacturing. You can actually start working on like creating new processes and stuff like that. It's really flexible. You can do whatever you want, to be honest. Yeah.
Not to interrupt you all, I'm going to put up the QR code, but people can keep asking questions, and I won't close the session down for the time being. All right.
So real quick, I just want to put out there, if you all have any questions, or like later on, if you want to just like chat about materials engineering in general, putting my email in the chat, feel free to reach out to me whenever you want to ask about anything. And I guess like one final note is that materials engineering is a very like intimate department here at Purdue. So if you like the smaller class sizes and if you like being able to grow with the same people throughout your degree, materials is a very, very close-knit department. I know all of my classmates. I've formed some pretty good relationships with team members, and it's pretty nice because I know in like aerospace and all that, there might be like 300 people in your graduating class, whereas for materials engineering, it's maybe like 40, 50, 60. So if you do better in the smaller settings and you really want to build those relationships among your classmates and your professors, materials engineering is a very good fit for you.
Yeah, and just to add on, if you don't know what you want to do, that's okay. It's the first semester fall. You have time to explore. If anything, I'll say MSE opens up doors.
Oh yeah.
And if anything, if you're scared that electrical engineering, mechanical, aero is gonna kind of narrow where you can work, maybe consider MSE, because now you can get into semiconductors. You can work at Corning using ceramics and stuff. Kimberly-Clark, 3M. You have a bunch of different industries that you can get into. So, if anything, that's pretty. I'm sure they do. They probably do like some sort of partnership with biomedical engineering and stuff. But yeah, definitely. If you're uncertain, maybe consider materials. Yeah. Definitely.
Oh God, watching Silence of the Lambs again.
I think we're about getting to the end. Like I said, reach out if you all want to know anything. I would love to help, love to chat. And also one resource that I heavily utilized when I was much younger, when I was a freshman, sophomore, reach out to people who are a couple years ahead of you, because the advice that they can give you can save you a lot of time if you were just to try to like do it on your own, so please reach out. All right, well, thank you. Have a great day, I guess.
Yeah, wait. I saw a couple. Wait. I want to ask these questions. Minor. I'm looking up the MSc minor right now because I forget what courses are involved. But yeah, definitely if you're interested in materials and kind of
it's
properties,
like 15
processing.
credit hours.
Yeah. I would say if you're interested and you have the space, why not? Why not? I know some chemistry students that wish they were in MSc, but they kind of went in too far and they can't get out. And they've done a minor and they're happy about it. Let's see, what kind of internships have you done and art? Ooh, here's a fun one. Internships, you don't always need to get an internship with a company. There's also different things like NSF grants at different colleges over the summer that lets you do undergraduate research. So there's a bunch of like nationally sponsored kind of opportunities abroad. Yeah, same with SURF. And you don't always have to look at internships. You can also look at actual research being done at different universities. I've seen stuff like 3D printing, stuff like that, blah, blah, blah. There's too many to remember. It's good fun. Let's see. I'm trying to see if there's anything else. Companies would say invest in a, what would you say? Companies, would you say invest in the employers? I don't know. I don't know, straight up. But if it interests you, just do it.
Companies that.
Yeah.
And you'll have plenty of time to figure out which companies do what. I've had 3 years of materials engineering to figure out which companies I want to work for, which companies have really good relationships with their employees, which is why I'm, interviewing with GE Aviation, because they treat their employees really well. So it's something that you'll figure out as you go along, definitely.
Let's see, does research look better than an internship or co-op? Ooh. I would say if you don't get internships or co-op,
do both. Do as man.
Yeah, do it. But if you don't get either internship or co-op, it's still fine.
For intern.
Yeah. Oh, sorry. I'll stop. Wait.
You can do research during the year as part of your coursework, I guess, and we'll kind of push you towards your graduation and count as credit for that. But internships and all that, really try to do something like that in the summer, at least get the experience, not only just to have a good resume, but to figure out what you want to do. Because even if you have an experience and you don't like it, it's just as important to figure out what you don't like as it is to figure out what you do like. And that's something that I feel is pretty underappreciated, because it's better to figure out what you don't like before you graduate than it is to start a job that you end up finding out that you don't like when you're kind of already locked in, and then it's this awkward oh, I haven't worked here long enough, but I don't really like it, but I can't quit because I'm too new to industry, so figure out what you like and what you don't like. So to me, that was figure out if I wanted to go into industry or research, which is why I've had both industry and research experience.
Yeah, I would say do your best to get internships and co-ops, but if you don't get them, don't be discouraged because they're very competitive things. Research is a good place to start because at least you have professors and you're still in school. So at least you're doing something at once. Like at least you're doing something and being productive.
And research will help you get internships.
Exactly. Looks nice.
And I've never had an issue with balancing classes and my research. It becomes part of your schedule, and you can do as many or as little as 3 hours a week to 9 hours a week in lab. And I've done this is my 6th credit hour in research, so I've done a lot of time in lab. It counts towards your degree, and so I really enjoyed being able to do this for my degree rather than trying to like take a tech elective for just like 1 semester, but instead have that ownership over my research, trying to help my research group, you know, getting published. That's pretty cool feeling when you're an undergraduate. So
your name's on the back. Yeah. Ooh.
Yeah.
We love that.
Yeah.
I would say definitely they encourage research because they do give you that 6 tech electives. I think something else that you normally don't do is, don't get through regular classes, is the actual process of going through these things, like doing a literature review and actually like trial and error and stuff, and also trying to present technical information to your professor and talk things out. It's a really creative time. There's no like schedule. You can do whatever, well, you can't do whatever you want, but you can go at your own direction and stuff with like
you have a lot of freedom
advice.
Usually.
Yeah, definitely.
Yeah. That's, and what you're saying about technical presentations, like when I started as a freshman, I couldn't even imagine talking about a technical topic for like 5 minutes in a row, 5 minutes straight, you know? And now I'm up here in front of my research group giving a research presentation for 45 minutes straight. And I look at the time and I'm like, wow, I still have so much more to say, you know? So you really get to see yourself grow a lot when you do research in terms of technical communications and all that. Tech electives are just courses that count towards your degree. Kind of, you have more freedom in choosing them. Like depending on which like kind of like sector of materials I'm more interested in, whether it's polymers, ceramics, or metals. The tech electives, you kind of get to like specialize in each of them. So like last semester, I took a super alloys tech elective with Professor Titus.
Professor Titus.
Did you take that class?
No, but I'm working with
You
him.
should have. Okay. Well, yeah, it was a very informative, very interesting class if you're into metals. But then also this semester I'm taking one based on polymer mechanics. So it's just it's more specialized. And then I see something about paid for summer internships. I've never heard of an engineering internship where you're not paid.
Yeah.
If you're not paid for an engineering internship, like you need to get with a better company because I mean, I'll be real honest, I got paid $25 an hour working full time this past summer.
That's more.
GE Aviation, I'm telling you, check it out if you like planes. But like as an intern, $25 an hour, that's a significant amount of money when you're broke in college.
Definitely. Yeah. I'm not even getting that much. Whoa. Is it important to be interested in chemistry to do MSE? I would say, how many of the classes in MSE actually involve much chemistry? Because I'm thinking it's more like more towards physics a little bit. Like I can only think like thermal.
Only a few.
Yeah.
I feel like for polymers, chemistry is more important. Whereas in terms of like metals and ceramics, it gets more to like the physics side of it amongst like atoms, but like polymer synthesis is a little bit of chemistry. There's like one like MSE organic chemistry class that's focusing on polymer synthesis, like I just said. But it's not necessary. And there are some people in the major who don't like chemistry and they still love materials engineering. It's just for me, I feel like it was the most applicable engineering discipline if you are interested in chemistry.
Yeah, I would say all the courses make me feel like a jack of all trades, to be honest. Cause like
You
we're
learn
able to
everything.
we do everything, to be honest. Cause statics is normally a mechanical engineering course. Thermodynamics, ours is more geared like chemistry kind of. And then we got like crystallography, quantum mechanics. That stuff's fun. We do a lot of things, like even electrical kind of things, semiconductors. That's kind of going towards electrical engineering. Really is a jack of all trades. It's fun.
Jack of all trades, jack of all industries.
Never get bored.
If you want to do something, if you want to work at a company, you can work there.
Mm-hmm. Just set your mind to it.
I think
Is that all?
covered a lot. If anybody has any last questions, put them in now or forever hold your peace.
Mm-hmm.
Or I guess not forever hold your peace. You can reach out to me, but
Yeah, or me. Yeah. Both of us. Yeah.
both of us.